and see how far we get in this topic, okay? So we talked about how to describe solution concentration. The important way to describe solution concentration using these problems is molarity, okay? And then we talked before about that. If you have a balanced equation that describes stoichiometric amounts of reactants and products that will form, then actually that's stoichiometry. So in this sort of problem, we're combining both solution concentration and stoichiometry in this sort of problem. Okay. So so why would you do this sort of problem? Well, it's kind of a practical thing. Either you are trying to get to the concentration of an unknown concentration, or you are trying to estimate what volume of a solution you would need in order for your reaction to go to completion. So I'll kind of show you what I mean about that. So molarity, by definition, is moles of solute per liter of solution. So actually that's kind of three numbers there. Molarity, moles of solute per liter of solution. Now we know that in algebra, if you can have one equation, as long as you have only one unknown, you can solve for that unknown. Okay, so my point here is if you know any two of those three quantities, molarity, moles, or volume, if you know two of those, you can just knock out the third. Okay, it is algebra. So, and you guys have been doing that actually in your homework for solution concentration homework. All right, so let's do one. So some of you recognize, and we'll be talking more about, I guess it really doesn't matter, but we have an acid here, actually sulfuric, that's sulfuric acid. You guys used that in lab the other day. You guys also used this in lab the other day. Okay, one of the cool things about acids and bases is they react to actually what we say neutralize each other. So they form, of course, water, and the other thing they form is some sort of salt. Okay, so that's just kind of a general look at this chemical reaction. This is balanced with coefficients of 1, 2, 1, and 2 across the board. Okay, so let's go down to the question. And a lot of times I will take these words and, like I've done before, put them underneath the species they talk about. So it says what volume, so I'll put what volume, and I have to skip ahead. What volume of NaOH, so I find NaOH, I put question mark, volume. What volume of NaOH is needed to what volume of 0.235 molar NaOH? So under NaOH, I'm going to put 0.235 m for molar. It is needed to react with, and then they give me some stuff about the H2SO4. They give me 35.0 milliliters of H2SO4, and the other thing they give me is the molarity, which is 0.108 molar. So I like doing it this way because then it almost, I won't say hits you over the head, but kind of hits you over the head maybe how you can proceed to do this problem. Do you see where of the two reactants, H2SO4 and the NaOH, we know more about the H2SO4? So honestly, you're going to see me work this in steps, and the first step is going to be come up with moles of H2SO4 using that information. That's pretty good. Step number 2, you're going to see on the next few slides, is I'm going to go then to moles of NaOH using stoichiometry. And when I have moles of NaOH, step number 3 is I'm going to use moles, and I'll just put a big M there for molarity, NaOH, to get to volume. I'll put arrow volume. Okay, that's kind of the 3 steps I'm going to do it in. You could do it all in kind of string them up, but you have to be more, what I say, explicit with the species involved. So anyway, this is how I prefer to do them right now anyway. So I'm going to title this moles of H2SO4 from the volume, 35.0 milliliters, and the molarity. So when we worked this problem before, we put the 35.0 milliliters over 1 as our first term. we can go from volume to moles using molarity, but we have to fix the milliliters. So the next term is going to be 1 liter over 1,000 milliliters. Notice that actually I'm dealing with both H2SO4 and NaOH, but as long as I title this, the blue and up there is the title, as long as I title this moles of H2SO4, that's fine. I don't have to say in 35 milliliter. So milliliters are canceled. Now I'm ready for the molarity. So now we put the 0.108 moles H2SO4, or moles H2SO4 over 1 liter of solution. So there's the molarity. So now milliliters cancel, liters cancel, we're left with moles of H2SO4, which is what we wanted to do in this first step. We always have to show all of our work and round according to what we're allowed, which is 3 significant figures. So 0.00378 moles H2SO4. And sometimes this is one of the problems where I really think it needs to, you kind of need to label what you're doing next. It will help you keep your wits about you. So sometimes students get in a hurry, but I would just really label the next step moles of NaOH. Okay, you don't have to say moles of NaOH and use reactive H2SO4, just moles of NaOH. So we're going to piggyback on the end of the first step. So we're going to start with the 0.00378 moles H2SO4 over 1. And now it's just a stoichiometric ratio. So you guys have gotten a lot of work at that. Okay. So we use the balanced equation. We put 2 moles NaOH in the top, and we put 1 mole of H2SO4 in the bottom from the stoichiometric coefficients of 2 and 1. And then we're done. And there's no uncertainty brought by the 2 or the 1. So again, 3 significant figures. Okay, that's just 0.00756 moles of NaOH. And then the last step then is always, this is where there's usually a different kind of question. Okay, so in this case we were after volume. Okay, so we're going to piggyback on our second results. So we're going to put that 0.00756 moles of NaOH over 1. And then we're going to introduce the molarity of NaOH. We're going to use what, the flipped version, yeah, because we want moles to cancel. So the flipped version of the molarity of NaOH, 1 liter of NaOH solution over 0.235 moles. So that, of course, is the molarity. And to me, since I think the question just asked for what is the volume, you have liters there, so you could be done. But a lot of times they want it to go all the way to milliliters. So if we were going to do that, we would put 1,000 milliliters over 1 liter, which is actually what I did. But again, you could stop right there with liters. 1,000 milliliters over 1 liter, so liters cancel, we're left with milliliters of solution. So again, we're allowed 3 significant figures. And I got 32.3 milliliters. So that's it. Solution, stoichiometry. But notice, and I think it said on the first slide, this only works if one, or in this case actually both of the reactants were dissolved in water. Okay, that's what you got to kind of count on. Let's do another one. The same reaction, but we're kind of mixing up what we know and what we're after. Okay, so what if the concentration of H2SO4, so what is the concentration of H2SO4? Find our H2SO4 and write question mark molarity. What is the concentration? if 25.0 milliliters of the solution, now that volume, 25.0 milliliters, is associated with the H2SO4. So 25.0 milliliters of H2SO4. If you're like me, sometimes you have to read this a few times. If you read the rest of the sentence, you're like, I know it has to be the H2SO4, because then it goes on to say, requires 27.7 milliliters of 0.444 molar NaOH. So in other words, there's one more volume here, and a molarity, and that is with the NaOH. Part of chemistry problems is just kind of finding your way through the problem. Delay. So under the NaOH, I'm going to write 27.7 milliliters. And also under the NaOH, I'm going to write 0.444 molar. And it's thinking. So in this case, we know more about the NaOH than we do the H2SO4. So actually, step number 1 is going to be use the volume and molarity of NaOH to get to moles of NaOH. Come on. It is Monday, but come on. All right. Let's try this. All right. So you got the 25.0 milliliters, and you got the 27.7 milliliters. Yay! And you got the 0.444 molar. Okay. So stepwise, question mark M over the H2SO4. So stepwise, you're going to see on the next few slides, I am going to take this volume and this concentration to get to moles of NaOH. Second step, I'm going to use stoichiometry to get to moles of H2SO4 using stoich. And the last step, once I have moles of H2SO4, I'm going to use, basically I'll show you in step number 3, we're going to take moles and we're going to divide it by volume, which is 25.0 milliliters to get molarity. All right, here we go. Solution. So moles of NaOH. We're going to use the volume, which is 27.7 milliliters over 1. And then we're going to use the molarity, the non-flipped version of molarity. Oh, no, we're not. We need to fix milliliters to liters. So the second term is going to be 1 liter over 1,000 milliliters. So then milliliters will cancel. Then we're ready for molarity. 0.444 moles NaOH over 1 liter of solution. So now everything have canceled except for moles of NaOH. Round it to 3 significant figures. I get 0.0123 moles of NaOH. Okay, so we're ready to piggyback onto the next step. So we go from moles of NaOH to moles of H2SO4 using the stoichiometric coefficients in front of those two things. So the second little calculation, we piggyback on the first calculation, 0.0123 moles of NaOH over 1. We want moles of NaOH to cancel, so we're going to put 2 moles of NaOH on the bottom, 1 mole of H2SO4 on the top. So 1 mole of H2SO4 on top, 2 moles of NaOH on the bottom. So moles of NaOH have canceled. We're left with moles of H2SO4. Again, 3 significant figures. I get 0.00615 moles H2SO4. And then if you've kind of diagrammed it, it makes more sense to me to look back at the original, what you're after. So now you have moles, and that's in 25.0 milliliters. So, and you're after molarity. So all we got to do is divide that moles by the 25.0 milliliters to get molarity. So to knock out the answer to the question, so 0.00615 moles of H2SO4 over 25.0 milliliters of solution. Now, molarity is moles per liter, not moles per milliliter, so we need to fix the milliliters. So we need to introduce a term 1,000 milliliters over 1 liter. And then units of cancel, we're left with moles of H2SO4 per liter of solution, and that's what we want. So it looks like 3 significant figures. So 0.246 mole H2SO4 per 1 liter solution, or simply 0.246 big M for molar. Remember, there is a little m too, so yeah, big M. H2SO4. And that's it. Another mole. That's a line in, I think, can't remember what musical it is. Oliver Twist. Mole. Ready? Okay. Another one. Actually, this piggybacks off the same problem that we just did, okay? So basically, they say we're going to take 25.0 milliliters of H2SO4 and 27.7 milliliters of NaOH. We're going to switch gears here in a minute and talk about titrations, which is what you're going to be doing in lab this week. And actually, can you see where these two volumes add together? So actually on the product side, in our solution on the product side, can you see where actually you have 25.0 plus 27.7 milliliters running around there in fluid? Okay, so where's the question? All right, and it says, it goes ahead and reminds us that we already knew this. We knew the molarity of the NaOH was 0.444 molar. Now, oh, there's the question. What is the concentration of Na2SO4? So question mark molarity. Question mark molarity. Let's see, if I was going to kind of tell you how we're going to do this, actually it's going to be in 2 steps. One step is actually we are going to go straight for the moles of Na2SO4 based upon the moles of NaOH you had on a few slides ago. We're going to use stoichiometry. Okay, we're going to use stoichiometry to get from the moles of NaOH to moles of Na2SO4. But the only catch here, if there is one, is the molarity of Na2SO4, the product, is equal to those moles divided by the total solution volume. The total volume, which is 25.0 plus 27.7. So here's what that looks like. Like I said, we're going to piggyback a few slides ago. We knocked out the moles that must have been in that volume and that concentration of NaOH is 0.0123 moles of NaOH. And the stoichiometry between NaOH and Na2SO4 is a 1 mole Na2SO4 per 2 moles of NaOH. So that's exactly what's going to go next. 1 mole of Na2SO4 over 2 moles of NaOH. And moles of NaOH cancel, and actually we're done. That's the step that's what we wanted to get to. So these moles are the same as the moles of H2SO4. Not so surprising. 0.00615 moles of Na2SO4. It is the same moles, isn't it? Because they're like a 1-to-1. Okay. So we're almost done. We're going to divide that by the solution volume. So like I said, if there is a catch, it's this, that you need to realize that on your product side, you're going to have the volume of both of your reactants. So 52.7 is actually the sum of 25.0 milliliters plus 27.7 milliliters. That's what's going to go in our denominator. So let's go ahead and take the ratio. Okay, so the molarity then is moles over volume. So we had 0.0615 moles of Na2SO4 divided by that 52.7 milliliters of solution. Again, we need to fix the milliliters into liters. So if we introduce 1,000 milliliters over 1 liter, we will do that. So now we have units of moles of Na2SO4 per liter of solution. Looks like we're allowed 3 significant figures. So I get 0.117 moles Na2SO4 per liter of solution. 0.117 molar Na2SO4. And that's it. He's getting out his notebook. That can't be good. Now here's the assignments that are due. We'll take a look at these. Pretty smooth at this. Watch, I jinx myself. Okay, so the first one looks like this, and you can see like in red and purple, I've gone ahead and pulled out from the problem what you know about the AgNO3 and the K2CrO4. Okay, so since you know more about the AgNO3, you're going to take the volume and the molarity to get to moles. Okay, second step, you're going to go ahead and use stoichiometry to get to moles of K2Cr2O7. So stoich. In this case, the K2CrO4, you're given molarity and you're asked to find volume. Okay, so in this case, you're going to use the moles you got from calculation 2 and the molarity to get to volume. That's what I'm trying to say there. That's 51. 52 looks like this, where again, you can just kind of pull out from a problem what you know and what you're trying to get to. So in this case, notice the calcium hydroxide, the CaOH quantity 2 is a solid. That's what little s means. That's fine as long as it dissolves in water, or you're fine. So you're after how many grams of calcium hydroxide are required to completely react with that given volume and molarity of HCl. So we can get moles of HCl from the volume and the molarity. And then we could get moles of calcium hydroxide from the stoichiometry, and then when it balanced it for you. And then we know once you have moles of calcium hydroxide from step number 2, you can get to grams using the molar mass of calcium hydroxide. That's a little different than what we had been doing. So the next one, what I did was to go ahead and I called it B, and up there in green is actually the information we know about this B, the second problem. This one's a little different. It's a little different because it's making you do a few more steps to get the moles of HCl. So if you read it a few times, notice to get to moles of HCl, you're going to have to use the volume of HCl, the weight percent of HCl, okay, and the density of the solution. Okay, so that will, I guess I would throw in, I think you're going to have to use the molar mass of HCl too. So, mm of HCl. So you do all that stuff, and you get the moles of HCl. From there, it's just the same as A. So once you have the moles of HCl, you can get to the moles of the calcium hydroxide using stoichiometry. And then once you have moles of calcium hydroxide, you can get to grams of calcium hydroxide using calcium hydroxide's molar mass. That's it. This one, okay, again, one of the reactants is a solid that dissolves in water. And for your NaOH, we're given volume and molarity and asked to find, oh, wait, no we aren't. In this one, notice that we don't have volume and molarity of the NaOH, but we have the total mass of the oxalic acid, the H2C2O4. So step number 1, to use that mass to get to moles. Get moles of H2C2O4 from grams. And use stoichiometry to get to moles of NaOH. Once you have moles of NaOH, you can divide those moles by that volume, which is 26.12, to get molarity. They're all just a little bit different. Yes. This is a good one. Basically, you have 2 chemical reactions going on. And I think later I call the top one with the calcium carbonate, the CaCO3, reaction A. And down here with the BaOH2, I call that reaction B. I've gone ahead and basically said that reaction A, you have excess HCl. If you read the problem, it says, all right, that little bit of HCl that's left over, it's going to go ahead and react with the B in the B reaction. And it wants to know what is the molarity of the original HCl. So I won't belabor this too much, but I kind of did it backwards. The green here is actually looking at B. And I said, all right, for B, we can use the volume and molarity to get to moles of BaOH2. From that, I can get to moles of HCl. And actually, I'm done for now. I can get to moles of HCl. Now, in the purple down here, I turn my attention to A, and I can get to moles of HCl there too. I can use I can get to the moles of the CaCO3 using its molar mass, and the mass given, 1.100 grams. And then I can use stoichiometry to get from the moles of CaCO3 to moles of HCl. So at this point, I have moles of HCl in A and moles of HCl in B. I would total those two things and divide it by the fact you started out with 25.00 milliliters of HCl. That's what I would do. There's definitely more than one way to skin this cat. And I think when you look, or if you do look in my answer key, I do it differently a few years ago. So, all right. On with the show. So, titrations. This is what you're doing on Thursday. So basically, for titrations, you need them both to be, you need to be able to do aqueous solution stoichiometry problems. Okay. This says a titrant, or a small amount of what we're going to call titrant, is dripped into, or we're going to call that an analyte, okay, basically to what we call the endpoint. And we'll talk about what that is. The way you drip in one solution is called a burette, or using a burette, excuse me. I have seen burette written, and I think I tend to write it this other way. Maybe it's burette. I think it's like this. It's more French. Either one of those spellings. But anyway, I want to turn your attention to this. This is called the stopcock. And I have an animation or a little video to kind of show you. Basically, if you see a burette and the stopcock is like that, then I hope there's no solution in it because it's totally open. Okay? So like that, it's totally open. If you take your stopcock and you turn it so it's a right angle to the tube, then it's totally closed. Anything in between is a little bit open. Okay, so that's totally open. So basically, you put your liquid in here, this is your liquid, and you let it drip out. That's it. Okay, and these actually are really nice. They have really small gradations on them. So I hope your vision is good for Thursday's lab. So what you put in the burette is called the titrant. Sounds official, doesn't it? And you drip titrant into the analyte. So I'll go ahead and show you if I have to like show a titration, or if I trying to think through even myself or something like that. Oh boy, that's awful. I know. Oh my gosh. You get the idea. That's my burette. And a very common place to put your analyte, this is supposed to be an Erlenmeyer flask. That is terrible, but that's my Erlenmeyer flask. Okay? So, and there's my analyte, and here is my titrant. Goodness gracious. So we'll see how this video goes. Okay, so here's the same thing in kind of still images. So we use a lot of clear liquids in chemistry. So of course, the stuff that's in the burette is clear and the analyte is clear. The thing right next to it, actually, that's a clear indicator. So the indicator you guys are going to use is phenolphthalein. Although it smells good, otherwise you can't tell the difference from water. Okay, so they're ready. It looks like the stopcock is kind of not all the way like parallel with the tube, but getting close. So in your titration, you're going to be able to kind of control the drops. We're going to basically do one fast and dirty, let it run in, and then we're going to kind of slow down near the end point. And so here actually you can tell the solution volume is increased, and see that pretty pink color? That's part of the art of titrating, is getting the color, which in your case is going to be pink too, it's phenolphthalein, and so it persists. So like the thing is, if it goes away between, I think it's like 30 seconds, your instructions tell you, then it doesn't count, so you have to add another drop of titrant. So, or you can add a part of a drop of titrant by using a stirring rod. Okay, so the titrations, the whole titration things, the fact that you put something in the burette, you put the analyte, you put the titrant in the burette, and you put the analyte in the Erlenmeyer flask. Okay, both of those things need to be dissolving in water. Okay, they both need to go into water or it's not going to work. Also, in order to do the calculations, you need to know how they react with each other, stoichiometrically. Okay. The reaction needs to be fast. Okay, like I think I might have mentioned in Gen Chem 2, we'll talk about how long it takes reactions to happen, you know, and they aren't always just instantaneous. And you can imagine if there's a delay, then you're kind of, I won't say entirely screwed, but you have to delay between adding your titrant to your analyte. You can't just assume that it's, you know what I'm saying. Reaction has to be fast, and the reaction has to essentially go to completion. Do you remember when we talked about the why you get low yields? And one of the things is basically there's like a two-way street. Reactants go to form products, and actually products go back to form reactants again. If that's the case, then you're in trouble too. Okay, it's not a good candidate for this method of analysis. The other thing is, and we used an indicator. You need to somehow know when you have dripped in just the right amount of titrant to use up all of your analyte. Okay, so I like to think of it, if you could actually see the molecules, the reactant molecules, uniting with each other. Basically, you have a lot of analyte molecules to begin with, and you're dripping the titrant molecules in there to react with them. So you need to know when you reach the end point. The real common ones are, I think it's on the next slide. Real common ones are the visual one, like phenolphthalein, and potentiometric, which is basically you look for the solution's conductivity. So we have two E points. We have equivalence point, okay, and then we have the end point. And hopefully they are the same. I'll kind of try to show you. It's funny because we abbreviate them EP. So that could be equivalence point or end point. I think it's usually end point or equivalence point. I don't know. But the equivalence point actually is when the observer, let's see, no, I got that wrong. The end point is when the investigator says it's over. Okay, that's when the investigator says, we're done. Okay, I've dripped enough titrant to react with all my analyte. The equivalence point is the real deal. Okay, if you could see molecule per molecule, you have used up all of your analyte. Okay, so actually we call these both EP. I think we call it equivalence point. Okay, so how do we know that you've added the right amount of titrant to entirely annihilate your analyte? Like I said, one is a visual indicator, and the other is, I mentioned, potentiometrically. Basically, you look for, it's the conductivity of the solution to know when you've used up all your analyte. So let's do one. Okay. All right, so in this one, let's go ahead and write underneath what we have. You guys have been using the pipettes, the 10 mil pipettes, which are standard. We actually have a 50 mil pipette in there. It's like, the bulb part's like honking big. It takes like forever to suck it up. But that's actually what they're using here. So with regard to the acetic acid, we know that there's 50 milliliters from a pipette. We put it in, you guys are going to be doing this too, and the video did this. Actually, the acid is going to be in your, is going to be your analyte, and you're going to put sodium hydroxide in your burette. Okay, so, and then notice that that's all we know about the acetic acid. It tells us that the sodium hydroxide is 0.1150 molar. And then down here, actually, it gives us the initial burette reading and the final burette reading. The initial burette reading and the final burette reading. So actually, under NaOH, how do I say? I'm going to just put volume, and I'm going to do it on the next slide. To get the volume dispensed, we're going to take that 23.90, and from that we're going to subtract the initial burette reading, 0.48. So actually that's going to be our volume dispensed, 23.90 minus 0.48. So now, oh, what was the question? Blah, 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 blah. Using the information to calculate the concentration of acetic acid. Okay, so there you go. Calculate the concentration of acetic acid. Question mark M, acetic acid. See how they just look so, they look so easy like that. So again, what we know most about is the NaOH. So step number one, I'll just put moles NaOH from the stuff. Okay. Second step, we get the moles of the other thing. In this case, CH3COOH using stoichiometry. Okay. And then step number three, let's see, we're after molarity. So it looks like we're going to say molarity is equal to moles divided by volume, which actually moles is from calculation 2, and that volume is that 50.00 milliliters. The other reason I like putting the information under the species is when you work these problems, there's like multiple volumes, multiple molarities, and if you just put it on there, you're like, oh, okay. So the volume of NaOH dispensed, like I said, we're going to get by difference. So 23.90 minus 0.48 is equal to 23.42 milliliters. Remember, we don't do a lot of subtraction in almost said astronomy. We don't do a lot of subtraction in chemistry, but when we do, we have to round according to decimals. So we're going to use that volume and the molarity of the NaOH to get moles. So here we go. Moles of NaOH. It's that 23.42 milliliters over 1. Of course, we need to fix milliliters to liters using 1 liter over 1,000 milliliters is our next term. Now we're ready to introduce the molarity of NaOH. 0.1150 moles NaOH per 1 liter of solution. So units that have canceled are milliliters and liters, and we're left with moles of NaOH. Rounded to 4 significant figures. I get 0.002693. 0.002693 moles NaOH. Now we said we're going to use stoichiometry to get from moles of NaOH to moles of acetic acid. So that's going to be our first term, then that next step. 0.002693 moles NaOH. And so we want moles of NaOH to cancel. So we're going to put, this is that boring stoichiometry. And you're like, is it even balanced? Yes, it is. It's balanced with coefficients of 1 across the board. So we're going to put 1 mole of NaOH in the bottom and 1 mole of CH3COOH in the top. And you'd be like, well, do I even have to show this step? And you know the answer to that. So units, we're left with units of moles of CH3COOH. So of course it's the same number. So that's equal to 0.002693 moles CH3COOH. And in this particular case, remember we're after molarity. So we're going to take that moles divided by the 50.00 milliliters. That's the last step. 0.002693 moles CH3COOH divided by 50.00 milliliters solution. Now remember, we're going to have to fix milliliters, so we can do that by introducing 1,000 milliliters over 1 liter. And then we can go with, round it to 4 significant figures. So I got 0.05387 moles CH3COOH per 1 liter of solution, or affectionately called 0.05387 molar, big M, CH3COOH. And that's it. So I went ahead and snagged this problem from the last slide. It wasn't to be cruel. It was to follow on the heels of what we just did, and I'll show you why. So problem 550 is also due. And you're like, chapter 5, what the heck? Well, let me show you. It looks like this. And you'd be like, well, that's what we just did. This is 50 in chapter 5. It gives you information about H2SO4. It's a titration method. So you have volume and molarity of H2SO4. You have volume of titrant, 23.31 milliliters, and you're supposed to get to molarity of titrant. So of course we can get moles of H2SO4 using volume and molarity. We can get moles of NaOH using stoichiometry. And then the last step, in this case, we're going to divide those moles that we got in step number 2 by the volume, which is 23.31, to get molarity. Easy cheesy. Do enough of them, you'll be doing them in your sleep. Okay? That's all I got.